Hey there, Calc folks, back here. It is post first class time, and I'm on here going to put together, I had promised out trying to get some videos out tonight for you on some lecture over the first section of material this semester, and that being we're looking at in chapter 6, like I had highlighted today in our meeting, is that we are kind of continuing our study of integration, picking kind of up where we left off in Calculus 1. Calc 1 really just introduced us to the fundamentals of the integration process. We're going to come back to the other side of those fundamentals now and look at using those fundamental skills to actually to do some application problems. And that's where chapter 6 here comes into play. All right, chapter 6 is application of integration. And we, I think, have 7 sections here where we have a variety of different application of integration presented to us, where we are looking at using these fundamental skills from Calc 1 that we learned about integration to help us perform some application problems, right? To help us through some applications. All right. The first thing I want to look at with you today is we are going to be looking at a little bit at motion in space, looking at motion along a linear path. And the first few videos here deal with motion in space along a linear path, where we're going to be looking at using integration to help us perform calculations like displacement and distance traveled by an object, and to help us derive, and that's a bad term there to use, to help us develop understandings of velocity from acceleration and position from velocity. So that is what's going to kind of develop here in this first section. We're going to go a little further into our understanding of motion in space, where we're going to study the concepts of displacement, the concepts of velocity from acceleration, and position from velocity, and then also look at distance traveled by an object. And along the way, we are also going to kind of throw in a side topic that, or kind of make a connection to a bit more of a generic topic, and this actually comes out in this set of notes. And that is this idea of net change, folks. And where we do start in chapter, in our study of the application of integration here, is with displacement and net change. All right, folks. Displacement is an idea that builds itself upon the velocity function, or we could even say the position function. All right, what we just take note, though, is note when the velocity function for an object moving along a linear path is integrated over some interval of time, right, the result is known as the displacement of the object over this interval of time. All right, in the study of motion in space, we were introduced to the position, velocity, and acceleration functions. If we take that velocity function and we consider integrating it over some interval of time, that does have an interpretation to it. That interpretation is what we call displacement. All right? And what displacement describes is the overall change in position for that object over this interval of time. How much does it change from the beginning of time, where we might start the stopwatch, up to where does it stop, and where how much does it change in terms of position from where we start the stopwatch to where we stop the stopwatch? There's going to be some change in position. All right, we might have to go from point A to point B, and how much did we change in that position? That understanding is displacement. Right, and the idea of displacement is it can be both positive and negative in value. That positive or negative aspect of displacement highlighting a change that's either in the positive or the negative direction. Right? And displacement even at times can be 0 in value. Right? Where the object is certainly moving, right, along its linear path, but it just so happens that the position from where it starts to where it stops are exactly the same, and really there is then no change in position over that interval of time, and the displacement would be said to be 0 in value. All right? But this is the value the calculation we're talking about here is displacement, and we get this calculation by integrating the velocity function. All right? I do bring this up in the formal definition, I do believe here, if I bring that into picture. All right? We might go ahead with the assumption that we have S of t describes this position and V of t describes this velocity of an object along a linear path with respect to time t. All right? If we go with those assumptions, then the displacement of the object over that interval of time t in that interval from A to B for time t describes what we call the overall change in position on this interval and is given by the following calculation. All right? The value for displacement is the integral from A to B for our velocity function with respect to t. All right? One thing I do point out is I do also have this other formulation for the understanding of displacement. It is also understood as S of B minus S of A. It's the S of B is position where we stop the stopwatch at, minus S of A, the position where we start our stopwatch at. Right? The change in position from where we start our stopwatch to where we stop our stopwatch it describes displacement. All right? And if we have our position functions, that is simply calculated by using S of B minus S of A in value. All right? But we don't always have displacement, we don't always have descriptions of position in our calculation of displacement. What we take note on here in this definition is that the calculation for displacement not only can be calculated using descriptions of position, but also can be calculated with the understanding of the rate of change in position or the understanding of velocity over this interval of time from A to B. All right? So when we integrate a velocity function from A to B, we are calculating what is known as displacement. We are calculating the overall change in position in either the positive or the negative direction. All right? You don't want to confuse that with the understanding of distance. We're going to get into distance here at the end of our lecture videos. Not in this one, but and just a couple down the line. I'm trying to keep these brief. But distance is going to look kind of similar to the calculation for displacement, but they do have different interpretations. They at times mean the same thing, but also at times can be very different from one another. All right? So let's look at an example, and I do give an example here. Consider the displacement of the object over time t in this interval from 0 to 4, right, whose velocity is described by the velocity vector, I say vector, I mean velocity function, v of t equal to 6t minus 3. All right? Well, if we assume distance is in meters, right, we're going to start also with that assumption. Displacement, as defined above, is nothing more than the difference of S of B minus S of A in value here, where A and B are the values 0 and 4 respectively. All right? So it would just be S of 4 minus S of 0, our position function evaluated at time 4, and our position function evaluated at time 0. All right? That difference would describe displacement. Now, we could calculate displacement if we had that bit of information. If we had the description of position, we could calculate displacement in that manner, but we don't. Instead, what we have is a description of velocity. But nonetheless, what the definition does tell us is that we can calculate that displacement calculation by actually also using our velocity function and integrating it over that interval from A to B. So here we are integrating, that is our velocity function being integrated over this interval from A to B, or this interval from 0 to 4. And this is a rather fundamental integration, right? If we go back to our fundamental rules, it's going to be a little power rule mixed with a difference rule, right? Where from our fundamental rules for integration, this integrand produces the following antiderivative, right? 6t, you bump that up to a power, right? Remember, integrals increase by powers. We raise that up to a second power, but we then have to divide by 2. So if we divide 6 by 2, that's where the 3 comes from, and then the t was bumped up to the second power. Minus, now technically we have a t to the 0 power here, right? That's equivalent to 1, but what we end up doing is bumping that up to t to the first power, which is just t, and divide by 1, which doesn't change our numerator at all. This is negative 3t in value for its antiderivative. Now recall, with that antiderivative, we now evaluate it across these bounds, which means we substitute in the upper bound for the values of our variable t. And 4 goes in here. That would be 16 times 3 is 48. Minus 3 times 4 would be 12. So 48 minus 12 would be the first evaluation, or would be 36 in value. And then notice this is a nice polynomial form where when we evaluate it at the lower bound of 0, it all zeroes away. And we have minus 0 in value. So 36 minus 0 is just 36 in value. So the overall displacement of this object on this interval of time from 0 to 4 is 36 meters. Right? The object exhibits 36 meters of displacement over this interval of time. More so because it is positive, right? It's moved 36 meters, or overall, in the positive direction, right? If it started at position 0, it's now at position 36. If it started at position 20, it's now at position 56 on the number line, right? That would be what the displacement is telling us. If it was negative in value, that would be in the negative direction, right? Thus, the object exhibits 36 meters of displacement, we might say here, in the positive direction, right? Is how we might state that out. Meaning it's moved 36 units overall in the positive direction over this interval of time, right? On the number line, over this interval of time. Let's put that in there to be a little clearer, all right? So that's all we're calculating for displacement there, folks, all right? Anytime we integrate the velocity function over an interval, we are calculating what is known as displacement, right? And it's the overall change in position, positive or negative change, all right? Or even 0 at times, all right? Displacement is itself a very specific case of a more general idea in the calculus. And that is what's known as a net change calculation. Displacement is a special case for a calculation known as a net change in a function over some interval, where we might say here the function is where we calculate net change for the velocity function. All right, or what we're calculating there is a net change calculation for I really should say position function, right, in terms of the general understanding, and we'll see that here in a moment, right? I do think that is what we see noted in our definition. Yes. We're looking at net change in some quantity, right? where that quantity, we can calculate it using integration by using the quantity's rate of change. So here we're going to look at net change in position, which is just displacement, right? Net change in position is just this calculation for displacement, right? So position function should be what's appropriate here, all right? And the net change in some quantity, and more generally speaking, right, the net change in the quantity Q of t over the interval from a to b for parameter t is given by this calculation, which looks a lot like the calculation we had above for displacement, but has been generalized to any quantity, right? Q of t. Any quantity being changing with respect to the parameter t. T being any parameter, not necessarily having to be time, like we see in the case for motion, right? We can calculate something similar to displacement, and it's what's known more generally as net change, right? Where that net change is the change in that quantity, Q of B minus Q of A in value, or can be found by integrating the rate of change in that quantity with respect to the parameter, the instantaneous rate of change given by Q prime of t. Remember back from Calc 1 that Q prime is the instantaneous rate of change in our function Q. Q here is our quantity Q, so Q prime of t is going to be the instantaneous rate of change, or what we just generalize as rate of change in our quantity. All right? Integrating the rate of change in any quantity over some interval of our parameter will lead to this generic understanding we call net change. All right? I do work through a quick example of just net change, and I let our quantity in this case be temperature. Right? We might say, suppose temperature is changing with respect to time, right? Where the rate of change in temperature, right, is described by T bar, or T prime of T, right? There's no bar there. It's T prime of T equal to sine of 2T, all right? And the question says here, or we're asked to determine the net change in the temperature over time t in this interval from 0 to pi. All right? Well, we note, given above here, that if we have the rate of change in some quantity with respect to its parameter, right, we can integrate the rate of change over some interval and calculate the net change in that quantity. So we should be able to integrate over the rate of change in our temperature to come up with a calculation for net change in temperature over this interval from 0 to pi. Right? In this case, the net change in the temperature over this interval is given by T of pi minus T of 0, right? The temperature at pi minus the temperature at 0, which, since we don't have our temperature's description, we just have its rate of change, we can calculate using the integration, right? The integration from 0 to pi for the sine of 2t, all with respect to that parameter of time t. Now here I let t be the parameter time, but it doesn't always have to be time, folks. It can be really any independent variable value. Excuse me. Now, keep in mind, this is a fundamental rule for our calculation here, folks. Sine of 2t, there's an antiderivative rule for that says that's equivalent to, I believe, negative 1/2 cosine 2t. Right? From the fundamental rules of integration, we should note that the antiderivative of the sine of 2t is negative 1/2 cosine 2t. Where if I now evaluated that at pi, cosine of 2 pi is 1, so 1 times negative 1/2 is negative 1/2. And we subtract from that, right, what we get when we evaluate this quantity at 0. Now at 0, that's the cosine of 0, which is 1 again. 1 times negative 1/2 is, again, negative 1/2. So this is negative 1/2 minus negative 1/2, which equates to 0 in value. All right? Which means, folks, overall, certainly the temperature is changing on this interval from 0 to pi. But how much did it change overall from the beginning at time 0 to the the end at time t equal to pi, how much did it change from that start position to that end position on that interval is nothing, right? In a sense, it kind of tells you that the temperature returns to the value that it was at when it started, right? It certainly fluctuates through that time, right, according to this rate of change, right? But cycles in a manner that it returns to its value at the end of that interval. All right? So that is net change in just another generic example here, folks. All right? These are two ideas just that we're going to kind of start off with here. They are some basic cases for the application of integration. If you integrate the velocity function, you'll always calculate what's this understanding known as displacement, which is really just a more generic, I really should say there, a specific case of a more generic calculation that's also just known as net change in a quantity. All right? So, folks, that does end the first video. We're about 21 minutes in. Hopefully you can give this a quick watch over before class tomorrow. And I'll see you in the next video. I want to get into a velocity from acceleration and position from velocity in my next video. And I'll have that out for you very shortly here. All right. See y'all then, folks. All right.